So all the questions from remote participating people are being collected on Slack, and Will Clarkson is following them. So a few words about the STARS, Milky Way, and local volume collaboration. It's essentially, well, what the science collaborations are has been recalled by Will Clarkson in his talk, excellent talk on Monday. Regarding our collaboration, it has the overarching goals of understanding the accretion history and structure of the Milky Way and the local volume, and the fundamental properties of their constituent stellar populations, including those near to the sun. Of course, everything that regards the stars is there. A lot of things that regarding variable stars is also there, even though there is a TVS collaboration, which is dedicated to transient and variable stars. Of course, there is a lot of synergy between this collaboration and TVS. The present chairs of the collaboration are Will Clarkson, Peregrine McGee, and John Gizis. John Gizis is about to step down. And we are presently, well, we try to keep at least a few working groups working. Those working or about to start working again are listed here. We have a solar neighborhood team, galactic structure and interstellar medium, one dedicated to the galactic bulge, then one for star clusters, the Magellanic Clouds, and near-field cosmology. There is also one regarding variable stars as probes of the Milky Way structure, let's say, which is about to be reactivated in the next weeks or months. Then we also participate in a lot of several task forces together with other science collaborations. I listed them here. I don't know if this list is complete or not, but we have the observing strategy, of course, crowded field photometry that we heard about that from Massimo Dall'Ora yesterday, I think. Then low surface brightness photometry, let's say, or the low surface brightness galaxies, and dark matter. About this session, it's a well-packed session with a lot of talks. So we have just 1.5 hours, so I will try to follow the schedule. This is the list of talks. And essentially, Will Clarkson is following Slack. Matteo Monelli is here telling if people are hearing everything on Zoom. Then Alessandro Mazzi, who is there, is taking notes. And of course, I thank all the people here, Marcello De Crescencio and you both for allowing this session to work. So, as I said, we have a lot of talks. All talks are 10 minutes. I will allow 8 minutes for talks and then 2 minutes for the two questions, essentially. And probably after 7 minutes, I will say, please close the talk, approach to the end of the talk. And then we have just 2 posters and they are maximum 2 minutes each. So that's all. Let's thank again all the people who are allowing this session to work. And the next speaker is Tom Wilson. No? Yes, Tom Wilson.
Hello, everybody hear me? Okay, there we go. Thank you. So first of all, I'd like to start with some thank yous to the organizers of the session, Will as well, and Leo, you all for being here, the STFC for funding this, and also because I uploaded an old version of this, George Beckett, Mike Reed, and Dominic Sloan Murphy for their help as well. They should be on the title slide, but they are not, sorry to them. So I'm going to talk to you today about the work I'm doing with the LSST UK consortium on the work of catalog cross-matching. And if you're not necessarily aware of this term cross-matching, and maybe you heard yesterday about list-driven matches in the Euclid session, the idea is you start with, say, a random data set. In this case, I'm using the WISE example because I have a nice picture. And you extract the positions and brightnesses of all of the objects in your image. And say, if this wasn't WISE, but it was Euclid, just to use the example from yesterday, and you wanted to match that to LSST in the optical, or perhaps TESS, because I have another pretty picture of the same bit of the sky, you could extract the positions and brightnesses of the objects in those two images separately. And then the idea would be which ones are the same object detected twice. And if I blink back and forth, then you see it's fairly obvious with the pictures, but we've only got these catalog lists. And you might have heard of this as, you might use this for your work in, maybe you've heard of nearest neighbor matching, where in my little circle here, you just pick you take your yellow object and you pick the nearest little black circle that's near it within some critical cutoff. And in sort of more computational parlance, in my little figure on the left, this is called counterpart assignment, where basically we want to know, is that black circle and that red circle one object with one gray star, or is it really two objects, in which case it would need two rows in our database entry, and therefore you'd see them as upper flux limits in the other data set. But the problem with the Vera Rubin Observatory's legacy survey of space and time is one of numbers. It's going to have a lot of stars, lot of galaxies, lots of objects. And so for my schematic on the left here, I'm showing, thank you to Leo for the TRILEGAL simulation, random bits of the galactic plane, the number of sources within two arcsecond circle. And you see that by the time we get to a single visit, well within a single visit upper limit, we get one extra source within every single one of these little nearest neighbor circles. And by full 10-year depth, there are 10 extra random objects within these circles. And now the nearest neighbor matching doesn't look quite so effective, does it? Because which one of those objects is the real one? You can't take the nearest one necessarily. So we extend to the idea of probabilistic cross-matching, where we can fold in first and foremost the uncertainty, the precision with which we know the centroids of our objects. Higher signal-to-noise ratio objects are known more precisely on the sky. So therefore we have these PDFs, these probability density functions that describe the certainty with which we think we know where this object is. And the other nice thing about this that we can do is we can include other pieces of information. So as we go to a more full Bayesian cross-match framework, we can include the photometry from our photometric catalogs, where we can use, and I have no time to describe this, so please ask if this is interesting. We can essentially use the constructive and destructive interference of the idea that every Gaia 15th magnitude object on the sky will have near it in those images, if you overlaid them as I did with WISE and TESS, a 15th, 14th magnitude IFAS I-band object. And it will have a random distribution of other, usually much fainter objects near every single one of those objects in the sky. And we can essentially build a classifier in a weak sense of match and non-match based on the photometry of these sources. But back to our astrometry, because that's the main driver of whether objects match or not, are they in the same place on the sky? What we actually care about is the probability that these sources are matched, the probability that they have their separation if we think they're matched. And to do this, we take these rainbow circles, which describe these beliefs with which we think we measured, the accuracy with which we think we measured the positions of these objects. And we can ask, what if the object's true position, which has to be the same for both of these circles, was that red star? Well, perhaps it was here, or it was here, or it was here, or it was down here. And if we do this across the whole sky and we marginalize out the true position of the objects, we convolve the two rainbow circles, and therefore we get the probability of separation of counterparts. And the key I want you to take away, if you take nothing away from my talk today, is that, well, first of all, we're calling these the astrometric uncertainty functions, these rainbow circles. and they do not need to be Gaussian. And as far as I can tell, pretty much throughout the history of probabilistic cross-matching have more or less always been assumed to be Gaussian, because that is the most common term introduced by the noise in the images, where you centroid, say, your model, you get some centroid of your model based on noisy data. But if we generalize this, what else can we do? And I turn here again to the WISE data set, which I use because it has about as many sources per PSF as LSST will do at full depth. So it's a very good example of an incredibly crowded data set. And I match it, I take a robust set of cross matches, which I believe are true, to Gaia, where essentially we can ignore the Gaia data set, incredibly precise precision. This is essentially just the true position for the sake of argument. And I plot two different distributions of these for two different sets of data in the black and red error bars. And they should, if they were only dependent on the noise in the image, follow that black dotted line. And I think that I can say with some confidence that they do not. But they do follow the line that I have plotted for both of them, the black and the red solid lines. And why is this? I turn back to this image of WISE, and again, I hope it is clear that these things are actually two-dimensional on our image. They're not point sources, as we always say they are. They have the point spread function. The optics blurs them out into some circle on the sky. You can see this for those 4 bright examples. And that then introduces an extra effect where they block out the light from fainter objects, where you can see a little hole on the right-hand side there, where there should be sources at the same density as in the halo around it, but there are not because they're absorbed into the brighter object. This then introduces a center of light perturbation caused by this blended, unresolved contaminant object, which if we do not model, we will get a high false negative rate, i.e. we will miss a significant number of matches. And in the case of WISE to Gaia, it is half. You lose 50% of your matches if you do not include this effect. And as I alluded to in my cryptic Slack message, if you saw that, just to say that this is not just a problem in the galactic plane. All of the unresolved point source galaxies out to infinity that WISE sees and both LSST will see as well cause this same effect in galaxies, as I show here a plot of essentially the same thing, matching Gaia to WISE in the galactic North Pole. So no stars in this image, effectively. Now it's a whistle-stop tour through a lot of the work that I've been doing over the past few years. And basically just to say this is a problem, but we think we've solved it. And we have developed and are currently developing a matching algorithm and matching service that will be hosted by the LSST UK Data Access Center. Why should you use our matches? Well, first of all, you'll find odd objects because we include the photometry of these sources. And you see a pretty schematic in the top right there. Because we have to model these things systematically, we have to Monte Carlo simulate them, you can get an idea of how much brighter these contaminants have made your source. You get these extra matches in crowded fields. As I said, 50% of Gaia WISE matches are missed, and we'll just be providing it as a service through the DAC. So you can just come to us if you want them for free. And because that is Leo looking at me worried, thank you for your time.
Thank you very much, Tom. Question, Mario on the back.
Thanks, Tom. This looks fantastic. Do you maybe have this in form of a Python or any other language library that could be used to integrate it with other tools?
Yes. So, oh, sorry, that's very loud. Yes. So sorry, that's the little logo you. Oh, it's gone. The Macau code is the software. It's Python with some Fortran under the hood for some complicated maths. It is publicly available, and the service itself will be run by LSST UK. But yes, it should be an installable package just as soon as I write some documentation.
So I ask now Will if there's some question on Slack.
I see no questions on Slack.
Okay, maybe we have time for a quick question. No? No? So let's go home. Let's thank again our speaker. And now next talk is by Annalisa Calamida. Please.
Can you use this?
I think so.
What? Now, yes. Hello, everybody. Thanks to the organizer for this amazing conference and giving me the opportunity to talk today. I want to present the results of this project that was started and led by Abisa and NOIRLab, and to which many other astronomers work with me, in particular from the Space Telescope, NOIRLab, University of Arizona. You see their names listed here. Sorry, I thought that it was 2023 already. I'm looking forward to LSST, so. Okay. So why do we need new standard stars for Rubin and also other future surveys such as Roman, for example, and DLTs? We need this because we require a network of standards that have, first of all, simple to model and non-spectral energy distribution. And then they must have high signal to noise, but also they need to be unsaturated in the observations. In particular, LSST is 8-meter telescope, ELTs are 40-meter telescope, and then we also have JWST, let's not forget about that. And we have to put these standards on a common flux scale. For example, it could be the HST flux scale. And the best standard that have all these properties that I just told you about are DA white dwarf. Why? First of all, they have a very simple spectral energy distribution. DA white dwarf are very hot, temperature hotter than 20,000 Kelvin. And essentially, they can be modeled with pure hydrogen atmospheres. And if you collect spectra for this DA white dwarf, you can easily derive their surface gravities and temperature by fitting the Balmer lines. And you can use these parameters to derive model spectral energy distribution. And in these experiments, we collected HSC photometry from the ultraviolet to the infrared. You see the 6 filters listed here, and you can compare this observation, so the observed spectral energy distribution, to the theoretical spectral energy distribution, and you can get a very good agreement, better than 0.5%, of course, modulo the reddening and the reddening law, that in this case we assume to be the Cardelli reddening law. You see from this plot, this is the scatter of the residuals from the photometry and the theory. And you can see that the scatter is better than 0.5% in all the optical filter. We have more problems in the infrared because we have more issues in the Wi-Fi camera 3 infrared detectors. For example, we have self-persistence and counter rate non-linearity. So we're still looking into these issues. Our network of standards of faint standard white dwarf includes 32 stars. 19 of them, as you can see from this height of projection, are in the northern celestial hemisphere, and 13 are in the southern hemisphere. And they all have surface gravity larger than 7 and temperature hotter than 20,000 Kelvin. And in particular, they are fainter than Gaia magnitude 15. Here you see also plotted the Casmir white dwarf as a reference. They're very bright in comparison. For these stars, as I said, we have HSC photometry in 6 filters from the ultraviolet to the infrared. And we also have spectroscopy collected with different ground-based telescopes that you see listed here. But then this was not enough to establish a network of standards because, of course, you need to make sure that these standards are stable. And these white dwarfs shouldn't vary because they're very hot, they're not in the pulsation instability strip, they're not magnetic, and we have spectroscopy, and there are no apparent companions. But still, they can have very, very faint low mass main sequence companions that you cannot see in the spectra or in the HST photometry. And so we decided to collect time series photometry with Las Cumbres Observatory in the G filter, since these are white dwarfs, with different cadences, because of course we have no idea about the period, so a cadence from minutes to months. And we use different variability indices to study the variability of the standards and also light curve. Here we compare, on the right plot, we compare the light curve of the white dwarf with the average light curves from a set of stable stars that are in the same field of view, since LCO has 15 by 15 arc-minutes field of view, something like that. And here we have a chi-square variability index of this white dwarf in red comparison to the other stars in the field of view. And as you can see, this star was presenting some kind of variability and was discarded from our network. In total, we discarded 6 white dwarfs that you see here at the bottom of the table on the left, and we kept a total of 32 white dwarfs that we named WDFS, which means white dwarf flux standards very easily. And we published the HST, I will tell you in the conclusion, but here I wanted to say that we published in this paper in 2022 all the light course based on the LCO photometry, and especially something very useful that is the finding charts. And these are based on HST imaging in the infrared filters, where you actually can see that there are a series of close by stars that if you're using these standards from the ground, you need to be careful and you need to be aware that there can be some very faint radar star close to the white dwarf. Close can be 2 or 3 arc seconds. So this information is also included in the paper, so you can select your favorite standard. So we established this network of 32 faint spectrophotometric standard white dwarf. So white dwarf flux standards that can be used to calibrate Rubin photometry, Raman, or even JWST, ELT's data. And they are distributed very homogeneously in the sky. So at least 2 of these stars can be observed from any observatory with a mass less than 2. And in these 2 papers in 2019, we provided HSC photometry and spectroscopy for the 19 stars distributed in the Northern Hemisphere, while in the recent paper that I published this year, we provide spectroscopy for the Southern white dwarf and LCO data for all of them. And a paper that will present HSC photometry for the other stars will be published soon by Axelrod et al. In 2023. And this paper will include also spectral energy distribution of these stars and filters calculated in different service systems, LON, pan-stars, DECAM, Gaia, etc. And the other thing that we are doing, we are serving these stars with STIS spectrograph on HST, because we want to, so ultraviolet spectra, we want to better characterize the extinction towards these objects. And also we want to verify that we're using a correct reddening law. And the other project that we have is to use HSC photometry in these 3 filters, so the B, R, and the I filter, to create a network of secondary standards which are close to this white dwarf, but have a different spectral type. Mostly they will be main sequence stars, so that we take also into account the effect of color on the standard stars. So that's all.
Very good, thanks, Annalisa. We have one question.
Yeah, thank you for this talk. When we are using the Oxtel with the spectrograph to monitor the atmosphere, we need, in fact, a lot of bright standards. I mean, with magnitudes lower than 12. Is there any effort in this direction also to try to increase the available number of standards? But well, we need also the SEDs, because this is for the spectroscopy.
Yeah, so like we have the CalSpec, do you know the CalSpec database of standards? Yes. Yeah, that are all quite bright, and they are mostly white dwarf, but there are also other spectral type, A-type, G-type stars that you can use. And we are putting these fainter white dwarf standards in the same system of the CalSpec white dwarf. So you can use, you know, the standards that you need. If you need bright standard.
But these are planned to increase the number of bright stars.
No, no, because we are going in the direction of, you know, the ELTs and, you know, JWST and Raman telescopes. So we are trying to increase the number of faint standards at the moment. But we are trying to improve the CalSpec database. In particular, now we are adding information on the stability or variability of all these stars with tests. So we observed some of them with tests, and now there's the plan to serve all the CalSpec stars with tests to characterize their stability. because if you need, sub% accuracy in your flux calibration, you need to show that your star is stable at the sub% level. So that's one of the things we are working on.
So I ask Will if there's some questions in Slack.
I do not see any questions on Slack.
Okay, maybe I have a quick question myself. I didn't see any standard in the galactic plane. Is that a problem or not? Right.
Well, usually, yeah, they have a higher. So this standard have a kind of low extinction, lower than 0.3. So, and they're all quite close by. They're in the disk, but close by, like less than 1.5 kiloparsec. So.
But the fact that we don't have standards on the galactic plane will be a problem or not for the calibration?
If the in the sense, like if we are observing, we were talking yesterday about the effect of the reddening. Yeah, it might be, but like it's very difficult, to observe stars there. So we're starting with this, and maybe in the future we can improve this, okay, set of standards. Yeah.
Okay, so
but the other thing, it was very difficult to find the set of DA white dwarf. So we had to use different surveys, like observation based on the VST as well, and VISTA, and we select mostly blue stars with high proper motion, and then we had to serve like many more. We had to collect spectra for like 100 white dwarfs to confirm that they were white dwarf and to select the best ones. Some of these end up to be magnetic stars or peculiar stars. So it was really, that's why this project took like years. It's not straightforward. Yeah.
Okay, let's thank Annalisa again. And the next talk is a remote one by Casmir Obasi. Are you there?
Yes, good morning, everyone. I'm here. Okay.
Just a moment, we are trying to find your slides.
Right, can I share from here?
Share your screen, okay.
Perfect, okay, just a moment. Oh, share screen.
Okay, we are seeing something.
Yeah, just a moment, please.
Okay.
And now?
Almost there. You should full screen mode. Okay. Okay, now it's okay.
Okay.
Please go ahead.
Good day, everyone. Yes. So today I'll be talking about the Halo globular cluster system of the nearest Seyfert II galaxy in Circinus. Now, this is part of my PhD thesis, among other things. Okay, globular clusters are very important and a very interesting astrophysical object to study because they serve as a unique astrophysical laboratories that we can test a whole range of theories. And the stars that make up globular clusters are nearly coeval, and they share similar chemical abundances, and therefore they serve as a very powerful tracers for galactic evolutions. And they are found mainly in almost every type of galaxies. For this project, I am most interested in studying the nearest Seyfert II galaxy known as the Circinus. Is a nearby spiral galaxies that is observed by Freeman, first observed by Freeman in 1977. This galaxy is also very active and is strong in X-ray and infrared, as you can see from the image in the right, see the box coming out from the galaxy. And it lies at the galactic latitude -4, and therefore it's been obscured highly by the Milky Way. And the extinctions in the central region of these galaxies are almost about 4 magnitudes, and therefore it's practically impossible to study with our conventional optical observation. But thanks to the near-infrared observation, like the Vista variable in PLAT extended survey that I'm using to make these studies, we can now be able to probe this galaxy and study the globular cluster systems entirely, because the Seyfert IIs are actually very bright in infrared. So the essence of this study is one, to carry out comprehensive globular cluster studies of Circinus and to use the result obtained from here to trace its evolutionary history, because it hasn't been done before. And for these studies, I am using the VVV survey, this is the Vista variable in PLAT extended survey, and complemented that data with the Gaia EDR3 to carry out the study. The photometries we are done using the extractors. Then after that, I did calibrated my data. I calibrated my photometry using the Alonso PSF photometry, and I also ensured that the calibration was were perfectly okay. For instance, I divided my magnitude. The magnitudes were divided into beams, and then calculated the median values to examine if there is no so much variation between my magnitude and that of the calibrator. And also the colors were also we also calibrated as well. So I also took up the magnitude beams in the colors and divided this by a beam of about 0.4. In all cases, there seems to be no clear color dependence, and my photometries are quite much deeper than what I was using for the calibration. So I was ready to start my search after correcting for the interstellar extinction using Schifrin and Franke extinction values. Then this is the way that I followed in carrying out the entire search for this globular cluster. Started with the photometries and the calibration. Then I looked at the parameter that were essential for my selection and the colors we selected, and combined the results with Gaia, then used all the Gaia parameters that were essential. At the end, we derived the results. For the color selections, I used the color range of globular cluster by 1 Getao, 2014, those globular clusters that were confirmed. So I chose my color based on that, the infrared color of 1 Getao in M31. And this was the selection. Then I compared that result with other confirmed globular clusters in other nearby galaxies like M31, M81, and NGC 5128. And you can see that the colors were in very good agreement. Thereafter, when I combined that with the Gaia catalog, there were some parameters in Gaia EDR3 that are quite very essential if you are working in extragalactic sources, especially to distinguish between the point sources and the extended sources. This was first pointed out by Vogt et al. 2020 in their paper, where they use the astronomical SX noise and the BPR PSX factor to select the globular clusters. And this method can actually be used to select sources up to about 125 megaparsec away. Now, I will state that this actually works effectively for sources that are above 10 kiloparsec from the galactic center, mainly in the halo. So basically, the idea is to they found a function that's always kind of discriminate between a point source and extended sources, in this case, the globular cluster. From these plots, which I tried to text this theory in some of the confirmed globular cluster. So in M81 and NGC 5128. So I start this selection. You can see, because I'm interested in my studies for all the sources that are above 10 kiloparsec, basically at the halo of my sources, which are the black sources. For the M31, you can see that the 3 points for the M31 that I have in this selection we above. In the paper of Vogt et al., they shows that some of these sources that are below this curve are actually misclassified galaxy, background galaxies, actually misclassified background galaxies. And for the NGC, you could see that most of the sources are above the curve. So this method was actually applied in my selection at the end. So at the end of the selection, I got about 78 sources that passed all the stringent criteria that we subjected our selection to. And I tried to compare the luminosity function of the sources with other globular cluster in other nearby galaxies. Luminosity function in the globular cluster can indicate path band together with that of Milky Way and M31. The figure shows from this that we only detecting sources, the brightest sources in globular cluster. This could partly be attributed to the high extinction level that are in that galaxy. Then with that, I asked the question, what could be the total number of globular clusters I'm expected to find generally, both in the halo that I've searched and the Bulge that I've also currently working on now. Now, using the equation given by Harris 2013, then we estimated that the total population should be around 120 plus or minus 40 of them. And the specific frequency we computed was around 1.3. This was still very consistent with what is consistent with the specific frequencies of globular clusters in spiral galaxies. And also,
Casmir?
oh yeah, no, yeah, I'll be done soon. So the color distributions was also looked at, and the color showed that the globular clusters showed by modality, and the surface density profile, it was consistent with what is obtainable for most of the globular cluster and extragalactic globular clusters. So this is the distributions of all the sources we got, and overplotted with the extinction values in the galaxy. And as you can see, most of our sources are within low extinction regions in this galaxy. So we are missing a lot of sources in the high extinction region. This is the first time we are carrying out globular cluster search in Circinus galaxy. And so far in the halo, we found about 78 globular cluster candidates that satisfy all our stringent criteria. And the globular cluster distribution is well described by primordial function. And we estimate about 120 plus or minus 40 globular clusters to be found in Circinus, and the specific frequency of 1.3. Thank you for listening. And if you have any questions, let me know. I also have some other papers in galactic globular cluster, by the way, in low luminosity globular clusters. Thank you.
Thank you, Casmir. We have time for one question. Will, is there any question on Slack?
I see none on Slack, but we could move on in the interest of time.
Okay. Maybe I make a quick question to Casmir. What are the plans for Rubin?
Yes, as I said, this is a very important, interesting question, because I'm currently trying to see if I can apply for the LSST catalyst. As I said, for Circinus galaxy, it's actually very practically impossible to study this source with the conventional telescope, but the LSLT, because of how deep the photometry will be, we can actually use try simulating using the LSLT GR and GR and I filters. Yes, we can be able to study, get to up to the ton of points of globular cluster in Circinus with LSLT filters. So it's something I'm also thinking about.
Okay, thank you very much.
Yeah, thank you so much.
Oh, let's thank again, Casmir. And the next speaker is Giada Pastorelli.
So can I use this, right? Almost. It appears. Okay. Okay. Okay, so hello everyone. My name is Giada, and today I'll talk about our in-kind contribution for LSST. This project is named Popstar LSST, and our PI is Leo Girardi. So we have team members mainly working on the Parsec code. We have other team members like myself and Michele and Alessandro who are here working on million stellar populations. And there are also team members working mainly on globular clusters and public outreach. And we also have a number of international collaboration. So what's the plan of our in-kind contribution? So we are non-directable software contributors. That means that we will provide simulated stellar catalogs for LSST. We already provided one first simulation a few years ago, and now we have a second simulation ready and available in our lab, Astrodata Lab. We also provide other related products such as stellar density luminosity function files that are already used in MAF since 2 years ago. You can find all the details in this paper that I listed there. And the plan is to provide other 3 simulations in the next few years. So the current workflow is such that we develop codes in Padova and Trieste, then we run them at the Dirac Institute in the University of Washington, and then the catalogs are ingested in our lab in Tucson. And we are also developing Jupyter notebook tutorials to explore our simulation in Padova. So our simulation are performed with the TRILEGAL code, which includes basically 4 galaxy components: the thin disk, thick disk, bulge, and halo, and of course also interstellar dust extinction. And we can also simulate external objects given their star formation history, distance, and reddening, like SMC and the LMC, for example. And here you see an stellar density map of our current simulation in galactic coordinates. The Magellanic Clouds are simulating using star formation history, a space-resolved star formation history. For the SMC, we use star formation history from near-infrared data from the VNC survey, while for the present simulation, we use the star formation history from ERIS and Zariski, but in the next simulation, we will use the star formation history recently computed by Alessandro Mazzi from VMC near-infrared data as well. So our LSST simulated catalog are complete down to 27.5 in the R band. This is the current sky footprint, as you can see from the figure, that will be updated following the latest recommendation to extend the survey coverage. And we use an ILPIX scheme with variable resolution based on surface mass density and extinction variation in each simulated field. Just a few words about the stellar model. So we simulate single stars using Parsec Colibri isochrones that includes all evolutionary phases from the pre-main sequence up to the AGB phase or the carbon ignition. And we also have post-AGB and white dwarfs tracks. We cover an extended range of initial masses and metallicities. And as I already said, we use TRILEGAL to produce isochrone and then simulated stellar population that can eventually be colored in over 50 photometric systems. Recently, we added also the binary evolution. We have a new module called Binapse in TRILEGAL, mainly developed by Piero Del Tio. And we can simulate both detached binaries and closed binaries. So what we have now are these simulated catalogs that are already in Data Lab. We have 10.6 billion single stars in one catalog, and we also have a second catalog with binary systems. So what you'll find is the photometry in all LSST and Gaia filters. Each simulated star has stellar properties, positional and kinematic properties, and we also have additional quantities for binary systems, including orbital parameters or stellar types, radial velocity, amplitude, for instance. So as anticipated, we are also developing a Jupyter notebook tutorial. So I'll go very quickly through the one that we have planned so far, so you can also see what's the contents of the catalogs. So the first basic example will be color magnitude diagrams and color diagrams. This is an example of the simulated star in the South Galactic Pole. And here you see S diagram actually color coded according to different stellar parameters. And this is the same stars from the South Galactic Pole, but in a color diagram. We will show how to combine single and binary catalogs. And we will give recommendation about the binary fraction to be used. And in this picture here, you can see some comparison with our simulated single and binary stars and some dark energy survey data. We will also show how to retrieve data of different fields in our simulation and how to do like star counts for them, also to compare how to compare them to other surveys. So this is an example of luminosity function in the LSST G band in different fields. The counts are performed with TRILEGAL, and there's a comparison with the DECAPS data and star counts from the GALFAS code. We also have eclipse in binaries. So here you see a density map of the predicted number of eclipse in binaries. We also have other kind of variable stars like Cepheids. So of course you can do star counts. This is an histogram of the predicted period for Cepheids. We also included long period variables, and you can hear everything about it in next talk by Michele. A few other applications are maps of crowding limits. Here you see an example for the Bulge region and the Magellanic Clouds for the air band and a specific value of the seeing. And we also provide maps of star to galaxy ratio, as you can see from the, this example here. So I'll conclude with what we have in preparation and the planned updates that mainly includes improved and calibrated models for different kind of stars like white dwarfs, AGB stars. We will include alpha enhanced model as well as rapidly rotating stars. And we are also planning to implement 3D extinction maps, star cluster, and also real kinematics based on SDSS data, as well as light curves for eclipse in binary, Cepheids, and LPVs. And as I said, we will provide to the community Jupyter notebooks in Data Lab. So if you have feedback and suggestion, they are more than welcome. And thank you.
Thank you very much. Giada, questions?
Do you also provide easy to use above the atmosphere SCDs? One of the things that one might want to do with a catalog like this is to actually simulate what the data looks like, where you have different pass bands, you have different CCD responses, you have different atmospheric responses. So you need the SCDs above the atmosphere to feed into an image simulator. Is that something you could easily code up from a Python module?
So you mean like, so we use stellar atmosphere models that are synthetic ones?
I just wondered what the interface would look like. If I wanted to run GalSim or something like that to simulate a field using your stuff, I need to know not the LSST magnitudes, because They depend on which chip it is and what air mass you're working at. So whether you've made it easy to get the SEDs in a way that someone else could use to do the rest of the simulation.
Okay, so we can actually, in principle, we can also provide SED. That's not implemented yet in the current simulation, but that's, in principle, we can also do that. So if it's something interesting that we can also provide, that could be added to our list of things to do.
Will, is there any question in Slack?
Thanks, Leo. I do not see any questions in Slack.
Okay. So,
just Thomas,
of course. Thank you for question.
So another question on the line of, can you do a thing that I would like, please? How easy is it to go deeper than the LSST detection limit? You've set 27.5, but to do my things where I'm simulating these sources to get the perturbation due to these objects, I need the sources fainter than the detected 27.
We can, of course, do that. I mean,
could you please? Thank you.
Yeah, sure. We can do that.
I think it only needs to be about 5 or so below 27.
Five below. Well,
is that a lot? Is that, you both pull faces? We can talk.
In principle, we can do that, but of course, you will have, in this.
It's a lot more sources. Yeah. We can talk offline.
But yeah, we can talk about it later. Yeah.
Thanks.
I would say for small areas, it's very easy. For the whole galaxy.
Once the whole sky.
Yeah. Okay. So, okay. Thanks again, Giada. The next talk is by Michele Trabucchi.
Can you hear me? Okay, thanks, Leo. And I'd like to thank the organizers of LSST at Europe 4 for this opportunity to present a little bit of my work. This is, of course, on the line of what Giada told minutes ago, and specifically the contribution concerning the implementation, incorporation in the simulations of variability features for Miras and long period variables. So, of course, this is something that is of interest both for the Milky Way collaboration and the TVS, but the direct implementation of this was in the simulation, of course. Briefly, long period variables represent the very final stages of the evolution of low to intermediate mass stars. And along the asymptotic giant branch, they develop large amplitude pulsation with periods of order of hundreds or even thousands of days. And they have a number of interesting applications. Few examples, they follow period luminosity and period age relations, so they can be used as distance indicators and to probe the stellar populations in the Milky Way and in other galaxies. So our aim is to enable this kind of applications within the LSST community by implementing variability properties in the simulations. Our approach is that of combining the synthetic stellar population models obtained with the TRILEGAL code with a grid of non-adiabatic linear pulsation models of long period variables. And we have been developing this approach since a few years. And this is an example of a result. It compares pretty well with the observations that you see on the left diagram of the period luminosity relations of long period variables in the Magellanic Clouds. So we were the first to produce a synthetic version of this diagram. And as you can see, for the overtone modes periods, that means blue, green, and orange sequences, we predict quite accurately the period luminosity relations, and to a level of detail that allowed us to show that actually two of these sequences, B and C prime, are actually due counterintuitively to the same pulsation mode that is the first overtone. So this unveiled a level of complexity that was quite unexpected for these stars. And this was also, what is that? Oh, okay. This was also confirmed by a later analysis of astrocosmology of red giant branch stars. So it's quite a good result. Another important point is this, you can see the distribution of the red points represent fundamental mode periods of Miras that are very interesting stars. And we quickly found out that with the linear pulsation models, we cannot reproduce this period luminosity sequence. So what we did was to compute another grid of pulsation models using a hydrodynamic code, so simulated the actual time-dependent dynamics of the layers of the envelope. And we were able to show that there is a systematic feedback between the pulsation, the large amplitude pulsation, and the envelope structure. The latter becomes more compressed with respect to the equivalent hydrostatic configuration. And the result of the increased average density means shorter periods. And that means that now we are able to predict accurate fundamental mode periods, and therefore to simulate accurately the period luminosity relation of the Miras. Direct implementation, direct application of this result was in a work that I recently published with Nami Molavi at the University of Geneva, where we simulated the period-age relation of the Miras, combining these models with state-of-the-art isochron models. And the result compares pretty well with observations of Miras with some estimate of age because of their membership in star clusters. We are also able to reproduce the actual distribution at a given age of the periods. So these are, of course, interesting applications. So summarizing, we are currently able to provide for a given combination of physical parameters of a star, the periods of the overtone modes from linear models and fundamental mode from nonlinear models. And the latter, unfortunately, are not yet incorporated in the simulation that is available to the LSST community, because this result came later after the finishing the simulation. But we are already providing easy-to-use prescription through the notebooks to compute these accurate periods. And our next plan include basically the computation of a whole new grid of these models, expanding on the space of stellar parameters, especially in composition, so to vary metallicity, enable us to study different astrophysical environments, focusing on carbon-rich stars, and so on. And the idea is not to provide only one period per star, as we're doing now, but actually to provide a multi-mode characterization, so both the dominant mode and all the excited mode with their instability strip. And we plan to provide some template curves of physical properties of the surface, so displacement, velocity, temperature, and so on, that we hope will represent the starting point to simulate photometric light curves in the LSST filters. And among the other things, plan to update on the prescriptions for various pulsating stars and other variability phenomena such as long secondary periods. And finally, I'm happy to mention that this project will involve a collaboration between the two LSST in-kind contributions, so ours and one of the creation in-kind contributions, because we plan to run these simulations, this hydrodynamic calculation on the HPC facility Bura at University of Rijeka in collaboration with Tomislav Jurkic, whose talk I encourage you to attend on Friday's European contribution plenary session. If you are interested in this, you should be, please download the PDF of these slides and click on the various links that are disseminated in these logos and in the previous slides. So I think I concluded my talk, maybe a little earlier, so we're given some time.
Very much, Michele. We are ahead of time. Questions for Michele? Will, is there any questions, Slack?
No, everyone is listening and convinced, it seems.
Okay, maybe I have a question. So, of course, that's applied for the Milky Way galaxy. You can simulate the stars in the Milky Way galaxy, but probably it's more interesting for the nearby galaxies where these bright stars will not be saturated. Do you have a list of the interesting targets for the models in the local group?
Well, whatever you like, normally. The idea is to provide these parameters for varying stellar parameters. They can be applicable to a number of astrophysical environments.
Okay. Thank you very much. Again, let's thank again Michele. The next talk is remote by Stephen Gough-Kelly. Stephen, are you there?
I am. Are my slides coming through?
We can hear you. Maybe you can speak slightly louder.
Yeah, is that any better?
Well, for me, yes. I think so. Okay, people are
great.
Okay, everything is set. You can start. Please go ahead.
Fantastic, thank you. So good afternoon, everyone. I'm Stephen Gough-Kelly, a PhD student at the University of Central Lancashire and a part of the Jeremiah Horrocks Institute. I'm also a junior associate of the LSST UK Consortium and a member of the M-Body Shop. What I'll hopefully be presenting to you today is our paper that was submitted earlier this year, which was titled Predicted Trends in Milky Way Bulge Proper Motion Rotation Curves with Future Prospects for HST and LSST, with collaborators at the University of Central Lancashire, the University of Michigan Dearborn, the UK Royal Observatory, and the Space Telescope Science Institute. The paper is available on arXiv and through that link there if anyone is interested in reading it afterwards. But I'm going to start with Clarkson et al. 2018, who used Hubble Space Telescope data of the sweeps field, which is a low reddening field towards the bulge close to L equals 0. And what they did was they looked at main sequence stars in the Hubble field and got their proper motions in the galactic longitude direction and plotted their proper motions as a function of distance measured in magnitudes here. And they were able to tag photometric metallicities to these main sequence stars, producing a population of metal-rich and metal-poor stars, where they found that the metal-rich stars had higher amplitude proper motions along the distance axis, producing this kind of asymmetric profile that you can see in the figure there. And it has larger amplitude than the metal-poor stars about the galactic center, which would be more indicative of faster rotation for the metal-rich stars, with 0 on this scale being approximately the galactic center. Where we came in is that we used a N-body plus smooth particle hydrodynamic simulation of a barred galaxy, which is qualitatively similar to the Milky Way. And what we did was we scaled and orientated this galaxy to be an approximate Milky Way and placed the solar position in there so that we could observe the bulge in the same way. And one of the earlier figures in our paper compares the simulation to the observations presented in Clarkson et al. 2018. And we found something qualitatively similar where we compared young stars with the metal-rich stars and old with metal-poor, and found qualitatively similar trends that the metal-rich stars or the young stars had higher amplitude proper motions on either side of the galactic center compared to the old metal-poor stars. Now, because we're using a simulation, we can actually plot spatial distributions of these populations, young and old, and look at the spatial distribution of their density and their velocities. So if I look at the left column of this figure here, where we're looking at the young stars, the yellow contours follow density, which you can see is elongated, and their kinematics, which we're looking at galactocentric radial and tangential motions. Both of those motions have quadrupole features, which are indicative that these young stars are on bar-like orbits or bar-supporting kinematics. The middle column here, which are the old stars, the density contours are still slightly elongated, but you can see that the kinematics are much more rounder, they're more uniform, indicating that they don't support the bar feature. So knowing these underlying intrinsic velocity distributions, do we expect that the proper motion rotation curves will look the same if we look across the entire bulge region? Well, what we first did was made predictions for HST data, where if we take HST data in 3 other low reddening fields, such as Stannick's window, Batty's window, and the Ogle 29 field, do we find the same rotation curves? And the answer is no. Close to the minor axis, where Batty's window and Stannick's windows are, which is close to sweeps on the minor axis, they have quite similar rotation curves in the same way that they're kind of asymmetric and that the young stars have higher amplitude motions. However, away from the minor axis, the Ogle 29 field shows a different rotation curve. And this is due to the young stars not just necessarily rotating faster, but their bar kinematics are orientated in such a way that they project onto proper motions in the kind of way that we're predicting here, which changes the profile of the rotation curves. So if we take a quantitative measure of how these rotation curves are different, we can look at the young rotation curve and subtract the old rotation curve from it and look at the differences between the two. And we can sum the differences across the distance axis. We get a quantitative measure, which we've called xi in our paper. And we can plot the distribution of xi across the entire Bulge region. Because it's simulation, we're not having to worry about kind of reddening or anything like that. We can do this across the entire Bulge. And this is what we produce. And if I draw your attention to these kind of higher amplitude regions over here, these coincide with regions where the young stars' bar velocities project onto the longitudinal proper motions and cause these differences in rotation curves, which we're detecting here. And this is where LSST comes in. LSST has the capability to produce a kind of a homogeneous map of the entire Bulge region. This was referred to as the definitive map of the galactic bulge in Ghazal et al. 2018, which is an LSST white paper. And they proposed two sub-surveys of the Milky Way bulge, one over the 10-year baseline of LSST, where we can get proper motions for stars across the bulge region, and the other being a multicolor, multi-band imaging of the bulge region down to fainter than the main sequence turnoff, to be able to do things like tagging photometric metallicities and to provide age estimates for these stars. We can then start to unwrap the evolutionary history of the Milky Way's bar bulge following these kind of techniques. An example of this is that's kind of already happening is the Blanco-Deccan bulge survey pioneered by Rich et al., who are already doing some great work in the bulge going deep, but they're using cross matches with Gaia EDR3. So LSST would actually provide us with a more homogeneous data set where we've derived proper motions and metallicities within the same survey. So thank you very much, and hopefully we get an image like this from LSST in the coming years.
Thank you very much, Stephen. Questions? Again,
I didn't quite understand what sort of accuracies you were hoping for in your proper motions. You were going down to 26.8, that's presumably 5 sigma, where the astrometry is not really all that good. So you're looking at what sort of motions that we have to reach? And at what magnitude?
The benefit of this is that if you've got enough stars in the kind of distance bin you're considering, the actual individual uncertainties on individual stars is not too important. I believe when we were trialing some of this, we were going down to 0.3 milliarc seconds per year as an uncertainty on values that have 2 milliarc seconds per year. So what's that, almost 10% or something like that? So it's 10% uncertainty on proper motions in the longitude direction is not too terrible. I've not looked at the
2 milliarc second positions are pretty hard from the ground, especially at any significant filter noise, right? So I think we'd have to look. I think I'd like to know exactly what you're expected from the data to see what we have to do. If we took enough epochs and root N work, that might happen. But I think this is a hard measurement. You're really pushing down into the atmosphere, into crowded fields.
Yeah,
I take your point. You can average over multiple points, but exactly how that works is not obvious to me.
Yeah, I would never suggest this.
Sorry, this is Will here. Perhaps I can stick my order in as well. Yeah, 0.3 milliarc seconds per star all over these regions would be quite an achievement. But we don't need to go quite that accurate, I think, to do this in a population sense. Even 1 or 2 milliarc seconds with a large enough population should be able to lift out the kind of trend that Stephen's talking about. But you're right, it does require further work of more detail to really sort of list out how well this will work field to field.
Okay. Will, do you see any question on Slack?
I do not see any questions on Slack.
Any other question here? So let's thank Stephen again. We have another remote talk by Nicolas Lodieu. Are you there?
Hello, can you hear me?
Okay.
Yes, do you see my slides?
Yes, we can see your slides.
Okay. Shall I start?
Maybe speak louder.
Okay, can you hear me now?
I will say yes.
Okay. So, okay, good afternoon, everyone. I would like to thank first the organizers to give me the opportunity to give this talk. Today, I would like to tell you about our goals to use the fantastic LSST data set to study the metal poor substellar population. And I will talk on behalf of our group at the ISC in Tenerife. So first of all, I would like to mention that the substellar population, and in particular the metal poor one, are very critical objects to study the galactic structure and the chemical arrangement of our galaxy, because their lifetime is very long. And so they really represent reservoirs of pristine material. Now, I would like to highlight this plot where I'm showing the luminosity of L and T brown dwarfs as a function of different colors, optical, infrared, and mid-infrared colors. In the blue, I show the L-type brown dwarfs, and in orange, you have the T-type brown dwarfs with a non-parallaxes, either from Gaia or from the ground. And we added a special object as a red dot, which is WISE 1810, that was discovered in 2020 by Schneider and collaborators, and for which we recently measured trigonometric parallax. And as you can see, this object, for example, on the right-hand side plot, it looks much bluer, so most likely a metal poor, but in other colors, he has a very peculiar colors, sometimes redder or sometimes similar to what we know about solar metallicity brown dwarfs. So now, so far, what we know about metal poor stars and brown dwarfs, that we don't have any metal poor brown dwarf with metallicities below -1.5 dex. What we have so far is a T8 companion to Wolf 1130 at the metallicity of -0.64, which is metal poor, but not so metal poor, at least to my opinion. Now, as I said, we have this object, the WISE 1810, which is most likely the first true metal poor brown dwarf with a metallicity below -1 dex. And we determine its distance to be 9 parsecs thanks to trigonometric parallax. There is also this object called the Accident by Kilpatrick and collaborators last year, which is a possible Y-type isolated metal poor brown dwarf, but we don't know the metallicity of this object. So now this is what we know now. What will LSST be able to do? We expect that LSST should be able to find all the M subdwarfs up to about 1 kiloparsec if we use R-band detection. If we consider now LSST for L subdwarf, you should be able to see them all the way to 30 parsec. But if we remove the conditions on the R and I detection, so we use dropouts, then we should be able to see them much further away. So in the case of WISE 1810 at 9 parsec, considering that this is classified as a T0 subdwarf, which is a preliminary classification, considering that we will detect it only in Z and Y filters in a single LSST exposures, we should be able to find these objects out to 50 parsecs. Now, if we go to much cooler objects, T8, so several hundred Kelvin cooler, and possibly 2.5 magnitudes fainter or even fainter than that, we should be able to find them up to 50 parsecs, but in the final 10-year LSST images. And again, only in the reddest filters. So what we want to do in the future with LSST is to actually look for high proper-motion brown dwarfs, as we did for WISE 1810 that was discovered thanks to WISE and the multiple epochs provided by this mission. If you look at these top images here, where we have an infrared image taken in 2010, you have WISE 1810 here above the two bright objects. And if you look 10 years later, this object has moved quite significantly to a different position because its proper motion is larger than 1 arcsecond per year. Furthermore, we want to use LSST to complement the Gaia at fainter magnitudes and get the parallaxes or the distances of these type of objects. Just as a reminder, WISE 1810, thanks to ground-based data that we obtained, if you look at the bottom left plot, for example, you can see that as a function of the time passes, we can see variations in the difference in the right ascension positions above 100 milliarcseconds, which places the object within 10 parsecs. So it's a very important addition. And because of this Z-band magnitude at 20, it's easy to detect on LSST single images. So we should be able to measure parallaxes for this type of objects. What we also plan to do is to cross-match LSST with Gaia to find the brightest brown dwarfs or subdwarfs. But we also want to do it with visible and infrared surveys, as we did to search for M subdwarfs. We did that in a paper about 5 years ago, where we defined some photometric criteria. And thanks to spectroscopic follow-up of all our candidates, we could show that 90% of them are indeed truly M subdwarfs based on their optical spectra. We also try to look for cooler subdwarfs using a combination of visible and infrared surveys. That was a work by our postdocs in Wazang, who found several tens of subdwarfs, classified them spectroscopically, and even defined a classification for this new type of objects. And of course, LSST will allow us to go much deeper than current optical surveys to complement the deep infrared surveys. But what we are very much interested in is LSST and Euclid, because one of our team members is the PI of the Independent Legacy Survey team dedicated to ultra-cool dwarfs, Eduardo Martin. And as you can see on this figure, there is a significant overlap between both surveys that was discussed already during a parallel session yesterday, so that don't need to repeat that. And just as a publicity, we have a Spanish virtual observatory archive on ultra-cool subdwarfs that we try to maintain to basically have the list of known M and L subdwarfs. What we are currently doing is to cross-match visible and infrared surveys, including Sloan and Pan stars in the optical, and Euclid's and the Vista Hemisphere survey in the infrared to look for L subdwarfs. As you can see on those plots, there is a significant overlap between all these surveys. We are talking about more than 10,000 square degrees, and we found several hundreds of candidates that are plotted here in the right ascension versus declination plot, and also in a color plot on the right-hand side. The photometric selection that we made so far is based on the colors we know for this type of objects, based on our previous work. And so this is a paper that we have in preparation. We also have a preliminary spectroscopic follow-up in the infrared to classify these objects. We used specs on the IRTF. We also used the EMIR spectrograph on the 10-meter GTC telescope in A Palma. And we got some preliminary spectra of a small subsample of candidates. And finally, I just want to say that we have also an interest in the time domain astrophysics. And we are thinking about the potential of LSST to detect microlensing events produced by high proper motion brown dwarfs. Again, taking the case of WISE 1810, which is moving more than 1 arcsecond per year, and that is located in the galactic plane. These are the type of objects that we need to monitor to see any possible variation in their photometry, because this is an independent way to measure their masses, in addition to looking at binaries, for example. And so this is very important to measure the masses of these objects to better understand the population. And so I just finish off with this slide where I'm showing the members of our team. Just want to highlight the PhD thesis by Yunyan Zhang, whose thesis is actually dedicated to metal-poor brown dwarfs. And this is a link to my website if you're interested in any other work that we are currently doing at the RIC in Tenerife. So with this, I take any questions that you may have. Thank you very much for your attention.
Thank you very much, Nicolas. Questions? Giuseppe?
Thank you very much for the talk, very interesting. I have just a suggestion in the sense that this is a very, very hot topic. And indeed, this is one of the driver of the Mikado Maori at ELT, because obviously the field of view is going to be tiny, but it's going to be very deep. And indeed, they are interested, there are teams interested in detecting the transition from hydrogen burning limit to L-type and T-type in nearby stellar systems. That is also a sound complement with what you have already mentioned, because in that case, they are all located at the same distance. So it's something that might be worth also to take a look.
Yes, we are looking at, mainly in that case, I was talking about isolated objects, but we're also looking for companions, which is an independent way to look for these type of objects, because you know the metallicity of the primary star. So that's very important, because as you know, it's very difficult to actually measure the metallicity of M stars or brown dwarfs.
Will, is there any question on Slack?
We do have a Slack question from John Gizis. I'll read it out. It says, what are your thoughts about spectroscopic follow-up of the new LT subdwarfs?
Yes, that's a very difficult topic, obviously. Some of them will be covered by Euclid, because there is a slitless spectroscopy in the infrared. And then we will have to most likely wait for the ELT and the very large telescopes.
Okay. Thank you very much again, Nicolas.
Thank you very much.
The next speaker is John Gizis, who's online, of course. Let's wait for the slides. Hi, John.
Hello, you can see my slides now, I hope?
Yes, and we hear you. Okay, so you can go ahead, please.
Okay, thank you. So this is some work that we did for the science optimization strategy work. And we selected brown dwarf astrometry as a science case. Of course, we know that Gaia has done a wonderful job basically mapping the whole stellar content of the solar neighborhood. And so here on the figure, you can sort of see this exquisite luminosity function, but you can also see from the error bars, over here on the right, that it sort of falls apart below the hydrogen burning limit because of the magnitude limit. And so LSST's even original science case, included the idea that it would be able to do parallaxes sort of for sources that are too faint for Gaia. And we wanted to explore that a little more. This is, I think, a really exciting science case because it's a test not just of the initial mass function, which we have lots of ways to get a handle on, but it really probes the sort of stellar, or if you prefer, substellar evolution and cooling of these objects and the atmospheric properties. And so here, for example, on the right, shows you sort of one of the current best cases of sort of the 20 parsec sample, where they've actually done sort of a 2D luminosity function. But notice the scale here, that's not a log scale, by the way. That is, really 4 objects per bin. And of course, you just saw in the last talk, there's sort of a similar color magnitude diagram plotted as points. So what we would really like, is many more objects per bin. And that means we sort of have to move out of the star by star parallax case and try to get many of them with LSST. And so we developed a sort of a very simplified brown dwarf model in order to compare observing strategies, but not really taking into a lot of account of subtleties that of course will be extremely important. We'd allow every brown dwarf at a given spectral type to be the same magnitude, even though same absolute magnitude, even though of course I just showed you in the diagram that they aren't. And so for basically, you can imagine you do the survey at a given point on the sky, you get something like the curve I show you here, which is you sample many different parallax factors. And so then of course you'd have to scale to the distance, you have to scale it to the distance of the brown dwarf, and you have to add in the astrometric errors. And basically the idea here is that with the Z and Y filters, there's every prospect of getting hundreds of measurements, which should be good enough to beat down, as Robert mentioned, the individual noise of a single measurement and get after parallaxes. And so the results, can look something like this. This is the version 2 cadence map. You can see the updated one. Of course, we do much better in the deep drilling fields, but those, actually probe a tiny volume, so they're not really much use for this science case. The important thing is sort of the wide, fast, deep area on the sky. And so by adding up, the distance for each spectral type that you could go out to get a signal to noise of 10 and the parallax for, you can get an estimate of like the total volume that will probe for brown dwarfs. And, I would say it's pretty encouraging. This is the simulation of the volume for the old V1.7 simulation and then multiplied by the current best estimate of the number of stars per cubic parsec at each spectral type. And so you can see that, you're approaching 1,000 objects per spectral type bin around the hydrogen burning limit, meaning the early L dwarfs. And then for the much more exciting sort of L T dwarf transition, you're still at the sort of 50 to 100 objects per bin. Of course, our current Poisson noise is built into this luminosity function. So, again, you don't have to take the details too seriously. The point is just how that should do. And generally speaking, it looks like most observing strategies work well with this science case. But of course, there are tensions, basically depending on what you decide to do early and late in the night, because that's when you have to be looking, so to speak, overhead to measure the parallax signal. So if you're chasing objects that are rising or setting, then that can, and you do that on many nights, that can really hurt this science case. But otherwise, things look pretty good. So probably it'll go down by 5 or 10%, as the real compromises are made in the survey strategy. But this is sort of order of magnitude, probably roughly correct. So I think it's a very exciting prospect. Of course, there will be many more brown dwarfs that don't have parallaxes, right? That are photometrically selected. We're not talking about those here. We're just talking about parallaxes with a signal to noise of 10 or greater. So that's it for this talk. I think it's very promising, but of course it will emerge much later in the survey. Any questions?
Question by Giuseppe Bono.
Very nice plot. And I appreciated your effort to remain within the range of the brown dwarf with parallaxes. But obviously the big question that I would like to lead with you is, what about the Y type? Do we have any chance to detect some of them, or is according to your simulation, or is it just they are too faint? What is your
Well, I stopped at T9, but for T9, I think that they are so faint that you basically are measuring only things within 10 parsecs. So then you have to ask yourself, you know, are there undiscovered Y dwarfs within 10 parsecs? You know, with all this work with Ys and stuff, you know, and so maybe there'll be a handful that are detected in one way or another. But I suspect, you know, that's a small enough volume that if you're interested in it, you could do it on your own, right? You know, if the number is going to be of order 2 or 5 or something like that, that you can do, I don't think you need LSST for it. So I think you really, you know, T8, T9 really falls off very rapidly. You get to very small numbers. For parallaxes.
Okay, Will, is there any question on Slack?
No.
Okay, I have maybe a very quick question is that you probably should look at the numbers of these very faint dwarfs in open clusters in the Milky Way, because we now know how deep you'll go for hundreds of open clusters and probably will have a lot of members in them. So, okay, that's my comment.
Yeah, I agree.
So now, thank again, John, by the talk. We have two very quick poster presentations. The first one is by Monica Jurkovic, who's online. Let me just remember that these posters are available. If you go to Slack to our channel, you see the program that we'll put there. And if you look at the bottom of the program, you'll find the links to the complete presentations of the posters. The complete presentations have 5-6 minutes. What we'll see now is just a small, very quick 1 minute, maximum 2 minutes presentation about them. Monica, are you there? Monica? Okay, you're there, but we don't hear you. Monica? Ah, okay. We are trying to fix this. Just a minute, in our Slack channel. Yeah, for the channel of this session, you'll see the program and the links to the posters. Yeah, we now hear you. Speak louder, please. Ah, no, we don't hear you. Sorry.
In the meantime, all the posters, the 5-minute talks of the light posters of this or all the other sessions are on the YouTube channel of the website. So you can find the version also through the YouTube channel.
So is it fixed? Can you hear me now?
Yes, now we hear you. Quite
great.
Cool.
So I'll talk very quickly. So this is just a pitch to introduce anomalous Cepheids and type 2 Cepheids as possible distance indicators. So this is not a new idea. This is not like I have invented the hot water. These are different type of Cepheids. So anomalous Cepheids are somewhere in the intermediate mass, intermediate age range, and they are low mass stars. And type 2s are even lower in mass, closer to our libraries, but they form a very separate period luminosity relations, which you can see here for the ogle, and also you can see this for the infrared. And also we have the period luminosity relations for these stars in the bolometric magnitudes. So I just pitched to you the idea that maybe when you classify these stars and you use the simulations that do separate them because they can be important. Thank you.
Unfortunately, we didn't see your slides, but I think it's not a big problem because people now know how to see the complete presentation. So the next poster is by Nadia Blogoro. Sorry.
Yeah, Nadia Blagorodnova. Yeah, so I recently started at the University of Barcelona as the PI of C3PO, which is an ERC funded project. And here I'm going to make a small description. So the why of this project is that we want to understand unstable mass transfer. And unstable mass transfer is key to the formation of common envelope, which we know it's a necessary phase for the tightening of the orbit and creation of gravitational wave sources and high energy phenomena. So what I'm proposing here is actually to use observations of luminous red nova transients that we know are associated to stellar mergers. But it's not enough to observe the merger itself, such as this VA38 MON that we can see here. But to understand unstable mass transfer, we need to predict these events because the unstable mass transfers is what leads to the merger. So in a pilot study that we did using Gaia data and CTF data, we localized stars, progenitor stars that we were very likely to undergo unstable mass transfer. And these are the stars between main sequence and red giant branch that are very quickly expanding in radii and therefore are likely to start this unstable mass transfer towards the companions. So after selecting the progenitors, we looked at their temporal evolution and we selected candidates that would brighten very quickly. So why I'm excited so much about LSST is that because right now we only scratch the surface of the iceberg using the time domain surveys because they are too bright. But with LSST, we will be able to go well beyond the waterline. And we not only will observe the transients, but we can also observe the progenitor stars, and we will see in real time how they go brighter and brighter, so that for the first time, we will be able to observe the unstable mass transferring happening with our eyes. Thank you.
Nadia, is there any very, very quick question to Nadia or Monica? No? So, okay, I think we just thank again all the speakers of the session. It's now time for coffee, and I invite you to discuss further all the presentations we saw here during the coffee break, because unfortunately we don't have time during the session for the discussion, but we can do that during the coffee break. Thank you very much.